All right, following examples are more advanced ones. So we want to apply L'Hopital's rule to find limits of those expressions. Well, we need to rewrite expressions a little bit before we apply L'Hopital's rule. So basically we have product of two functions. When you plug in or when you use unbounded negative number, basically we have infinity times. Well, from this graph, when your x approaches negative infinity, this function will give you 0. So basically we have product infinity times 0, and it's quite difficult to find a limit directly. To apply L'Hopital's rule, we need to rewrite the expression, because basically what we want is some fractional expression like a over b. The given expression is just a product. So we want to have such a thing. So what we can do, well, we are given product a times b, like that. And we rewrite this expression intentionally to have some fractional expression. So a over 1 over b, of course, or you can rewrite it as b over 1 over a. So there are two ways. So let us use this rewriting to have fractional expression. So this limit is limit of x squared over 1 over e to the negative x, or 1 over e to the x. Or you can put it like this. So we have fractional expression a over b. And as x tends to infinity, negative infinity, we have infinity over infinity. Well, the graph of this function, 1 over e to the x or e to the negative x, as your x tends to negative infinity, this function will give you infinity. So basically, this is infinity over infinity form. So we are in good position to apply L'Hopital's rule. Okay, so L'Hopital's rule say this limit is derivative of this guy over derivative of this. Well, this is just e to the negative x. So derivative of this is e to the negative x again, but you will need negative. Good. So this negative symbol will give you, again, negative infinity time over negative infinity. Again, this is indeterminate form, so you apply L'Hopital's rule again. Derivative of this is 2, and derivative of this is again e to the negative x, but the sign is plus. So we are ready to write down the limit, because as you see, this graph says that this function is unbounded as x unbounded. So 2 over infinity or 0. So one quick remark is that for this given product a times b, there are two ways to have fractional expression, a over 1 over b or b over 1 over a. So here we took 1 over e to the x in the denominator so that derivative of x squared becomes simple like that. If you use the different direction, like e to the x over x to the negative 2, the derivative will not give you simpler expressions. So the quick warning is, well, you need to choose direction carefully to see when you have simple expression after taking derivatives. Well, simply, if one doesn't work, you take the other direction. Number 5 is also interesting. If you plug in 0, basically we have 1 minus 0 to the 1 over infinity or infinity. So we have kind of indeterminate power form. So for this limit, we need to use L'Hopital's rules as well as logarithmic differentiation. So for this expression, so we let this function y, 1 minus 6x to the 1 over x. So we are taking this entire function for this y, and then we take ln of both sides. So then we have ln of y is ln of the right hand side, and using the property of ln, you take this power down here, 1 over x, ln 1 minus 6x. As you see, we have fractional expression automatically. Ln x over x. Very good. As x approaches 0, we have ln 1 over 0. Again, this is a 0 over 0 form. So we are in good position to apply L'Hopital's rule to this expression. So we are taking limit of ln y so limit of this expression now that we have 0 over 0 form, we apply L'Hopital's rule. Derivative of numerator is 1 over 1 minus 6x times negative 6, and then this denominator will give you 1. Actually, we are ready to find the limit. So 1 over 1 times negative 6 over 1, or negative 6. So we applied L'Hopital's rule to find the limit of ln y, and we want to find limit of y itself. So we need one more step. So to figure this out, we can use a couple of ways. So first way is we can use property of the continuous function. So what we have is, well, limit of ln y is negative 6. Well, ln is continuous function, so you can switch the order. So originally we had ln followed by limit. Now that ln is continuous function, you can take limit and then ln. Actually, this limit of y is what we are after, right? Limit of y. That's what we are after. But we know this guy must be negative 6. So ln of something is negative 6. So you can use the property of ln to see this limit of y is e to the negative 6. Well, basically what we are using is, if A is ln of B, then B is e to the A. That's what we are using. Or secondly, we can use some rewriting. So limit of y is, for any number or expression, this is e to the ln y. So we are using the property that whatever equals e to the ln whatever. And as we know, this is e to the limit ln y. Again, we are using the fact that e to the something is continuous function. You can change the order. So e to the something followed by limit is e to the limit of something. And as we computed, the limit of ln y is negative 6. e to the negative 6. The same result, of course.